In continuation to our earlier module, that is module 7, where we discussed about application of digital human modeling software in agricultural sector. Now we are going to discuss this software's application in aviation and aerospace industry. So first we are discussing a review paper written by Sangjog et al. 2015. The title of the paper, Towards Virtual Ergonomics, Aviation and Aerospace. So in this review paper, authors described how various virtual ergonomics evaluation techniques has been used by various researchers all over the world in aviation and aerospace industry. Sangjog et al. In their review on application of virtual ergonomics in aviation and aerospace industries mentioned that DHM technology has been used in assessing various human factor issues in those industries. Those human factor issues include reach and accessibility in aircraft cockpits, creating accurate posture libraries, performing vision analysis for pilots, determining design modification to accommodate female users, because many of the cockpits are initially designed for male users. Predicting probable pilot behavior in proposed cockpit design, simulating airflow and heat transfer in fighter plane's cockpit, assessing comfort of airplane passenger seat, maintenance studies, human spaceflight training, verifying component accessibility, and investigating impact of spacesuit parts and harness, spacesuit parts and harness, etc. In this review paper, researchers described virtual ergonomics approach in aviation and aerospace industry with the following subheadings. They discussed about how digital human modeling software can be used for cockpit, flight deck and crew extension design, and also aircraft passenger seat comfort evaluation. They also mentioned regarding aviators' musculoskeletal load fatigue due to protective equipment, design support in space station, maintenance application in aircraft and space station. So with these following subheadings, authors actually categorized the available information in these fields. I mean, who are the various researchers, what type of research they have conducted related to these topics. So that information has been categorized and represented here. Researchers presented critical review leading to a comprehensive knowledge body about application of digital human modeling in aviation and aerospace industry. They identified, so in this research paper, following all these aspects of aviation aerospace industry, so researchers also mentioned that which are the areas where further research can be carried out, that avenues needed to be explored, and provided future research direction aiming at aviation and aerospace completely human-centric. So in this review paper, authors compared the traditional ergonomic evaluation process versus modern digital human model or CAD-based evaluation method for ergonomic evaluation in aerospace and aviation industry. Based on their comparison between these two, one is traditional ergonomic evaluation process and next another is virtual ergonomic evaluation process using digital human modeling software in aviation aerospace industry. They concluded that the traditional approach for ergonomic investigations involving costly physical mock-ups and trial with real humans can easily be replaced by or effectively replaced by evaluations facilitated by digital mock-ups and digital humans. So if you look at this image, so in this image authors depicted the conventional ergonomic approach. So how ergonomics approach being adopted for evaluation on various facilities and human factor issues in the aerospace industry and aviation industry. So they mentioned about few research paper, laboratory setup with replicated aircraft floor and adjusted gradient. So the and reference provided. Similarly, push pulling in a full size trolley in the laboratory. Full motion helicopter simulator used for data collection trials. Then they also showed that ergonomics approach has also been used for helmet configuration with night vision goggles, battery pack and counterweights. Research flight simulator being also used. So in this way, through this image, authors tried to demonstrate that various ergonomics aspects are being evaluated in aviation aerospace industry from the long back, following traditional real human and real product based methods. But with the time, CAD software came, and now most of these evaluation are being performed in CAD's virtual environment using digital human modeling software and CAD prototype of the Q cabin or cockpit. So these are the few examples how various researchers have used digital human modeling software for their evaluation, ergonomic evaluation of the cockpit or spacecraft. So first one, human spaceflight training. So digital human model is used for spaceflight training. Then cloth and equipment mannequin in a helicopter. Analysis of multi-crew workstation. While more than one crew are there, then how they are interacting with each other and how they are resolving the conflicts in operation. So all these are being studied. Then many researchers have used digital human modeling software for comfort analysis, vision analysis in the cockpit of the aircraft. Similarly, geometry of the cockpit and how human is interacting with the cockpit model, that is also been studied by researchers. Now we are moving to the next research paper. This research paper is by Zhou et al. 2013. Title of this paper is A Fatigable Musculoskeletal Model for Prediction of Neck Maneuvering Loadings on Aviators. So, a fatigable musculoskeletal model for prediction of neck maneuvering loadings on aviators. Researchers studied cervical musculoskeletal load and fatigue on military aviators during aerial combat maneuvering. So while this aerial combat maneuvering is being performed, then how is the cervical musculoskeletal load and fatigue that are studied by these researchers, Zhou et al. 2013. A whole body articulated multi-body model with detailed neck musculature was utilized to predict joint loads, muscle forces and fatigue of a fighter pilot during high G maneuvering. Two flight postures named Look Ahead and Check 6 are investigated to understand their effects on neck loadings. So here it is shown in this image that two different posture which were assessed in this particular research. So one is look ahead while the pilot is looking forward, and another is while the pilot is looking at an angle, that is check 6 posture. Feedback control algorithm was used to derive joint torques and consequently optimal muscle forces in order to maintain desired postures during high G maneuvering. Researchers incorporated a dynamic muscle fatigue model based on the fatigue rest recovery mechanism to predict fatigue of muscles responding to dynamic loading condition. So while there is dynamic loading condition, high G maneuvering is going on and there is change in the G value, then how the musculoskeletal load at the neck is being changed, that was studied. The neck biodynamic responses such as joint dynamics, muscle forces and fatigue levels to the applied aircraft acceleration for the posture under study are measured and compared, that whether there is any difference. Because two postures are studied, so whether between these two postures whether there is any difference in terms of neck biodynamic responses and also whether there is any change with the time. The result indicated that the postural variations during high G flight significantly affect the cervical musculoskeletal loads, and the muscle fatigue plays an important role on muscle force capacity and overall activation pattern to generate required joint torque for posture maintenance. So from these images, so one A is the upper one A, that is the look ahead posture in both the panels. Similarly, check 6 posture, the bottom one check 6 posture. So muscle activity at the beginning or starting time, then this is the scenario in both the postures, whereas after 300 seconds, how is the muscle activity, how is the muscle fatigue. So that is shown. So due to this G force, as it is mentioned here, the postural variation, due to these two postural variation, so you can see that muscle activity or activation level is different. Similarly, muscle fatigue level is also different after a certain time. Next paper title is Application of Digital Human Modeling and Simulation for Vision Analysis of Pilot in a Jet Aircraft, a case study. So this was reported by Karmakar et al. 2012. So researchers stated that the operator or pilot face a rapid decision making problem under extreme time constraint situation like navigating task in a jet aircraft or in any other information processing task of high density workstations. So in high density workstation, while pilot or operators are involved in processing various information and their cognitive load is high, that time it is very important at least there should be reduced physical workload, or we have to make the system in such a way that physical workload should be at minimal level. The researchers demonstrated how vision analysis tool of digital human modeling software can be used effectively for ergonomic evaluation of pilot's vision in a jet aircraft in virtual environment. For this purpose, 2.5th percentile, 50th percentile and 95th percentile digital human models are created. These human models are actually representative of smallest, average and largest Indian pilots, and those models are interfaced with the jet aircraft cockpit and various ergonomic evaluations are performed by using JAX software, and the vision analysis within and outside the cockpit are assessed. So not only inside the cockpit but also outside the cockpit view field are also evaluated. And for positioning digital human model on the ejection seat, design eye point approach was followed as it is mentioned here. So DEP method was followed for positioning all sized pilot models in the seat. So here it is showing that digital human model has been kept on the ejection seat, and various vision related evaluation is being performed. So this is the analysis with view code. Researchers stated that it is possible to determine the position and alignment of different control and displays based upon their priorities in the view field with the vision analysis tools of digital human modeling software. The vision analysis in the cockpit was carried out in following condition. So in this research paper, researchers carried out visions of the pilot with this condition, with 15-degree view cone, then 30-degree view cone and 40-degree view cone. So while there is variation in the size of view cone, then how the visibility is being changed or view field the area of viewing field is changed. That was studied. Analysis for blind spot are also done. Analysis for eye view window and analysis for obscuration zone. So if we look at the image, so here it is shown while vision is being analyzed with 15-degree view cone, then how much is the visibility of the displays. So this is the display, and on the display this portion is showing that within 15-degree view cone how much area of the displays is visible to the pilot. Similarly, while that view cone has been increased to 30-degree, then the visibility increased and this much is covered. But to cover most of the displays, actually pilot need a view cone of 45-degree. So within 45-degree viewing angle, pilot is actually able to see most of the displays placing in front. Similarly, in this research, researchers also found that while the pilot is looking forward towards the display, then through eye view window, this is a particular tool in JAX software, with that tool they identified that which areas is actually visible to the pilot. So that is coming in a separate window. This is that shown in inset. So while pilot is looking forward, then this area of the bow, mirror and display, head up display, that is actually shown in this inset image. Vision analysis in virtual environment with digital human modeling software has proved to be very effective for positioning different displays in the workstation according to the operator's requirements, anthropometry and targeted users, anthropometry of the targeted users long before the development of actual prototype. So following this research, researchers mentioned that digital human modeling software is very effective in creating finalizing the model of the CAD model of the cockpit before actual, because the analysis is possible in virtual environment before developing the actual physical prototype. Results of the present study would help in determining the optimal position of various components, particularly displays in the aircraft cockpit as well as any other workstation. A similar vision analysis approach can also be adopted for other types of workstations. So from this image it is visible that region of blind spot while the pilot is looking ahead on head up display. So we can create this type of blind spot zone, and it is from this particular research it is found that none of the display are coming within the blind spot area. So displays are actually positioned properly. Similarly, while the pilot is looking on the side control panel, then how much is the neck angle while the pilot is looking with 30-degree view cone on the side control panel, then that time body angle or torso angle, neck angle, so different body parts angle can be measured, and we can identify how much difficulties are there to visualize that side control panel. Moreover, authors or researchers also demonstrated that how various displays are obscured due to various control operation. Like while the pilot is operating this throttle, due to position of the throttle, this lowermost control panel is actually obscured. So obscuration zone tool of the digital human modeling software is very much effective for this type of study. Now we are moving to the next paper by Osterland and Lawrence in 2012. The title of the paper is Application of Digital Human Modeling and Simulation for Vision Analysis of Pilots in a Jet Aircraft, a case study. Researchers proved that the use of multi-object motion capture technology and digital human modeling tools in aerospace is a more cost-effective alternative in comparison to developing costly physical prototypes to provide a more efficient, flexible and responsive environment to change in the design and the training and proactive consideration of human factors concerning the operation of a complex launch vehicle or spacecraft. So, in these research papers, researchers demonstrated that how multiple object motion capture technology and digital human modeling software can be used together for evaluating various ergonomics aspects related to design, training in the operation of complex launch vehicle or spacecraft. United Space Alliance USA developed the techniques and tools for virtual evaluation of both spacecraft assembly, ground processing operation design and training on the Orion Cube module. So, various parameters of interest and benefits of spaceflight simulation training with virtual reality were mentioned by them, and here it is listed. So, it is good for familiarize and assess operational process, allow the ability to train virtually. So, from this system it is possible to go for virtual training of the crew or the astronaut, experiment with what if scenarios, expedite immediate changes to validate the design implementation. So, it is also possible in virtual environment for going immediate changes and validate the design implementation. 3D animation of post training assessment. So, following the training from the recorded 3D video animation video, then it is possible to assess that how was the training. Placement of avatars within 3D replicated work environment in assembling or processing hardware. So, it is also possible to place avatars or mannequin within 3D replicated environment in assembling or processing hardware. Providing the evaluators the ability to assess task feasibility and identify potential support equipment needed. Providing human factors determinations such as reach, visibility, accessibility. So, all these various aspects can be performed, can be achieved by this system. The deployed system utilized 26 high-speed, high-resolution Vicon cameras, Maya animation software, Jack ergonomics software, Anarch conversion and polygon reduction software, 3D motion building software, integrated into 4 high-speed 64-bit operating system platforms. So, this is the overall softwares and system description. To test the functionality of the laboratory and system, 4 different test scenarios are demonstrated. These are the 4 case studies which they perform to test the functionality of the laboratory and the system. So, first one is Orion Crew Module environment, Orion Crew Module environment control and life support system installation and removal. Second, Crew Module seat removal and replacement. Third, Orion service module, drain port accessibility and visibility. Removal and installation of Orion Crew Module station power transfer unit. So, these are the 4 cases where they deployed their system to find its functionality and feasibility. In CY 2010, United Space Alliance used augmented reality technology for human space activities by adding a head-mounted display to each actor. They found that the system would provide a level of human model simulation not yet discovered, providing virtual reality to both the actor within the real environment and virtual reality of the integrated environment. If we look at the image, so it is showing actors provide human in the loop simulated environment, Vicon cameras capture the stick figure, wireframe and Jack Live generate the avatars. So, insert this is the Jack Live software screen and this is the 3D motion analysis system. So with the Vicon camera, based on the position of the marker on the real human subject, the motion of the actors can be captured, and based on that motion, captured motion, JAC Live software can create the digital human model. And while these actors are performing their activity, the same thing, the same action is being demonstrated by the human models in the CAD environment. And in that CAD environment, while these digital human models are performing various activities, then various ergonomics aspects related to their comfort, related to their spinal compression force can be evaluated. Actors perform, here in this image it is shown, actors perform a T pose to calibrate the system prior to installation of the environment control and life support system unit through the crew module, crew hatch. So it is shown here. So the real process or real function, real activities performed by the actors can be various ergonomics aspects of their activities can be evaluated in JAC software. It is possible because their activities are being simulated in virtual environment, and in virtual environment with the ergonomic evaluation tool of the JAC software is enabling to assess various ergonomics aspects. So in this image it is shown simulated reach, operations and visibility with the specialized rubber suit called a self-contained atmosphere protective ensemble suit, provided insight into potentially required training. So it's provided insight into potentially required training exercise. So while it was simulated in the virtual environment, that while the astronaut or the crew members are wearing this type of space suit, and that time for performing various activity, what type of difficulties they are facing, and accordingly researchers realize that for this type of activities actually crew members or astronauts should be trained properly. Similarly, while the real actor performing some activity in real scenario, that is captured with the motion capture system, and the same is being transferred to the virtual environment of JAC software. And from the JAC software, it is very easy for going different types of ergonomic evaluation, at the same time to identify potential problem for this type of activities. If there is any problem related to safety or related to collision or related to space requirement, so all these aspects can be studied in virtual environment. So in this image it is shown removal of a large surface area panel required awkward positioning of the technician personnel's body, thus risking injury to themselves or the hardware. So these two images indicating two actors conduct a seat removal. So two actors here in the real scenario, they are performing seat removal activity, while observers, they are the observers, assess the safety of the personnel and hardware. So while the real actor performing the activities, the same is being simulated on the computer screen, and the observer from this virtual simulation can understand, can visualize that what type of problem, safety related problem the personnel can face during removal or assembly of the hardware. So this image showing astronaut crew members point of view while they are using head mounted display coupled with HEMF MAP system. So in this image it is showing crew member using virtual reality helmet and the Charlotte robot to practice mass handling. So why this type of head mounted display is there, at the same time the real operator is handling this type of robot, then the same information can be transferred to the virtual environment. So, the overall their system integrated this type of, as we shown, motion capture system, virtual simulation as well as virtual reality. So, these three things they combine together for virtual evaluation of the spacecraft or a launch vehicle with these 4 case studies as you mentioned earlier. Now, we are moving to the next research paper, application of human modeling in multi-crew cockpit design. This paper was written by Sun et al. 2011. In this paper, researchers evaluated the process conflict in multi-crew cockpit from the aspects of vision and accessibility of multi-crew design using digital human modeling approach. In this paper, researchers described the process of digital human model creation and controlling posture of the human model. They also discussed various theoretical aspects of multi-crew cockpit design in terms of the coordination process, the conflict during cooperation or coordination. During the process of multi-crew cockpit design, the researchers analyzed the process conflict. Mainly they concentrated on process conflict in coordination mode using 50th percentile digital human model. So, with 50th percentile digital human model, while they are evaluating the multi-crew cockpit design, they analyze the process conflict in coordination mode. Their assessment include whether the position and arrangement of the monitor was in the best field of vision, whether the position of the controller operated by right seated pilot, the pilot who is seated at the right side, this pilot while he is performing various controlling operation was inside the field of vision, whether the position of the controller operated by the right seated person was inside the field of vision, whether the result of operation was blocked during the process of operation by the right seated pilot. So, assessment include whether the position or arrangement of the monitor was best fitted for the vision. Similarly, while the right seated person is performing various activity, then the visibility of the left side pilot, whether it is being affected or not, that was also studied. The potential conflicts in the process of multi-crew coordination are identified during operation of devices of the cockpit by digital human model in virtual environment, and advices are given on the improvement of multi-crew cockpit design. The researchers concluded that the conflict could be reduced in cockpit and the safety and efficiency could be increased in multi-crew flight operation by digital human modeling based evaluation. Next research paper by Green and Hudson 2011. The title of the paper is A Method for Positioning Digital Human Models in Airplane Passenger Seat. So, this paper actually dealing with how digital human model can be positioned on the passenger seat. So, proper positioning of passenger mannequin on digital passenger seat is very crucial for evaluation of various human factor issues related to seated passenger in the airplane cabin, because seated passengers needs to perform various activities. For example, switching the light or changing the seat rest angle, backrest angle, and so many other activities. Researchers developed a method for positioning digital human model in a digital passenger seat based on their research on anthropometric and posture related measurements, along with establishing relationship between H point location, which they have mentioned as digital human model seat reference point with seat reference point. So by establishing how they position the digital human model, they position the digital human model based on the relationship of H point location of the digital human model or SRP location of the digital human model with seats SRP. They claim that the standard passenger postures identified in this paper is more accurate than the eyeball method and simple to implement. So, for this purpose 26 subjects are selected for whole body scanning based on their anthropometric similarity to idealized 95th percentile boundary mannequin groups to ensure a large variability of the targeted user group. So, they identified 26 subjects and took their body scanning because those persons are similar to idealized 95th percentile boundary mannequin groups. And this selection process actually ensures a large variability of the targeted user group. So, they scan the body dimension of 26 passengers while they are seated on the passenger seat. The subjects are scanned in various postures from seated erect to slightly slumped. The seated erect posture was used for the development of standard posture of the passengers. So, out of various types of postures, selected posture, finally the seated erect posture was used for development of the standard passenger postures. Additional anthropometric data collected by Faro 3D digitizing arm was used for direct point-to-point measurement among anthropometric landmarks and with landmarks on the seat. This data was used to determine the relationship of the subjects to the seat. For determining the definition of the subject's posture, a digital human model on each subject's anthropometry was created using Dassault System V5 virtual ergonomic solution. So, they use digital human modeling software, that is the Dassault System V5 human, to provide the subject's posture. Each digital human model was then positioned and postured to match the erect scan of the respective subjects. So, on the erect scan of the respective subjects or the passenger, so first what they did, they created the digital human model based on the anthropometry of the passenger, then superimpose the digital human model on the scanned 3D body scan image of the same subject or same person. After this superimposing of the digital human model on the scanned image, it was found digital human model in the standard passenger postures appear reasonable but don't have good alignment with original scan. Their proposed method for positioning and posturing digital human models in economy class seats are as follows. So, first identifying the SRP seat reference point of the seat, determining the seat reference point, that is the midway of the hip joint point or H point of the digital human model. So, SRP of the seat, SRP of the human model, and this SRP of the human model is the H point of the human model. Third, rotating the digital human model so that the hip segments matches the proper pelvic orientation with the scanned image. Moving and changing all other body segments to the joint angles determined from the scan or digital human modeling process. Creating and saving the final posture adopted by the digital human model and save it to digital human models library for further use. If you look at this image, so while normal erect posture is provided by digital human modeling software, then the scenario is like this. So, it is not exactly matching with the passenger seat, but the method which has been described in this research paper, if we follow that method, then the standard posture is actually matching with the seat profile. So, with this method, designer or engineer can easily provide appropriate sitting posture to the digital human model while they are interfacing the digital human model with the passenger seat. Next, we are going to discuss one more research paper related to passenger seat only. So, this research paper is related, the title is on the creation of 3D libraries of F-16 pilots in their crew station, method, development, library creation and validation. So, this was reported by Ouden Tuizen et al. 2011. The reported research was aimed to develop a posture library for SafeWork digital human being system. So, this research was actually aimed to develop a posture library for this particular digital human being software named SafeWork to reduce the errors related to initial positioning and posturing of the mannequin. Because if initial positioning and posturing of the mannequins on the seat is not proper, then the whole ergonomic evaluation in the F-16 pilot cockpit will be meaningless or useless. So, for that purpose, proper positioning of the pilot in the seat, ejection seat, is very important. The proposed method for providing posture to digital human model enable the mannequin to assume realistic posture by employing 3D body scan to real people in F-16 ejection seat. So, as we mentioned in the earlier paper also, so digital human model actually provided realistic posture by employing 3D body scan of the real pilot or real subjects. Posture library was developed for initial position and posture during reach, as well as to quantify the effect of restraint system and protective equipment in F-16 cockpit environment. 14 subjects from both sexes, male, female, and wide range of anthropometric shape and proportion variation are considered in this research. These 14 subjects participated in the creation of F-16 SafeWork posture library. The posture library development followed these following steps. So, first, scanning of the subjects in F-16 ejection seat to record position and posture data. Next, creation of SafeWork mannequins based on subject's anthropometry. So, first body scanning, second SafeWork mannequin creation based on the subject anthropometric data, and third is this digital human model has to be aligned with the scanned image of the person. So, align mannequin to scan, creation of SafeWork posture library. The library of 15 rich postures for SafeWork human modeling system developed from the present research would be used as a kind of fidelity profile that quantified and simultaneously accounted for the effect of restraint system, protective equipment and tissue deformation in the sighted cockpit environment, that is F-16 cockpit environment. So, these are the 15 postures which we are discussing. So, the 15 resulting postures of the library of each small mannequin are the combination of the 3 heights. So, they are reaching at 3 different heights at the top and in 5 directions. So, this is shown from this top view images. These 5 top view images is actually indicating the 5 reach direction. Similarly, the top 3 images is showing the side view images showing the reach in various heights. So, these 15 reach postures are actually developed out of this research, and these this could be used as kind of fidelity profile that quantified and simultaneously accounted for the effect of restraint system, protective equipment and tissue deformation. Based on the experimental data, it was concluded that the library was highly accurate and verified for positioning and anthropometric accommodation of mannequins on F-16 cockpit when using human modeling system SafeWork and the resulting posture libraries. So here it is showing that how that digital human model is created and positioned on the seat. So first, scanned image or body scanning data of the real pilot. Then on that body scanned image, digital human model is positioned, and this is the final digital human modeling posture. So on the scanned image, digital human model is superimposed and posture was given, and this is the final posture. Similarly, in this image, left the final alignment of the mannequins and subjects upper extremities using appropriate markers, resulting in an initial resting posture. So left side is the initial resting posture, and the right side, this image is showing the creation of a reach posture aligning the subjects and mannequins marker. So how this posture can be, this particular reach posture can be achieved? It can be achieved by aligning the subjects and mannequins markers. So around the the scanned image, there are markers. Those markers and the corresponding markers around the human model can be manipulated to achieve a particular posture. So this image already we discussed. Next, this is actually next we are going to discuss about a technical report by US Army Research Laboratory, and it was reported by Hicks et al. 2010. So title of this technical report was mentioned as an overview of human figure modeling for Army aviation system. So in this technical report, actually researchers described various human modeling system which have been used for Army aviation system in US Army Research Laboratory. Following their extensive review on application of digital human model in Army aviation system by US Army Research Laboratory, Hicks et al. 2010 stated that digital human model softwares or digital human modeling softwares has been used to assess and improve the ergonomic design and usability of all modernized Army aviation system, as well as to reduce analysis and development timelines. Army Research Laboratory Human Research and Engineering Director, known as ARL HRED, has developed a digital library of Army aviation aircraft and equipment to assess them in terms of human factors engineering design standards. So they developed a library for both Army aviation aircraft as well as various equipments, and those can be to assess them in terms of human factor issues. The modeling conducted by that laboratory has resulted in numerous system design improvements to meet the human factors engineering design standards. In the report, researchers mentioned that modeling results have been used by government and industry to improve the ergonomic design and system functionality, assess anthropometric requirements, and reduce analysis timelines. The report described the use of digital human model design and development of various aviation systems, including so this is the list, including various aviation systems. So they actually covered 8 aviation systems, which are UH-60M Black Hawk, CH-47D Chinook, Armed Reconnaissance Helicopter, RAH-66 Comanche, Army Airborne Command and Control System, Air Warrior Advanced Threat Infrared Countermeasure System, Common Missile Warning System for AH-64D. So digital human modeling software JAC has been used by ARL HRED in the development and testing of 8 Army aviation systems. As we mentioned earlier, to assess and improve the ergonomic design and system capabilities. So, if we look at this particular table, then we can find these are the list of 8 workstations where various ergonomic aspects are evaluated using digital human software. In the first one, RAE66 Comanche, researchers studied ingress egress analysis, crew station design, review mirror location, helmet integrated display, sight system, and helmet integrated display sight system analysis. The next workstation, that is UH-6TM Black Hawk, researchers studied crew station design, anthropometric design analysis. In the third workstation, they evaluated egress analysis. In case of air barrier, anthropometric design analysis was performed. In common missile warning system, AE-64D, CMWS, sensor field of view was evaluated. Then advanced threat infrared countermeasure, in this case maintenance analysis was performed. The next, armed reconnaissance helicopter transportability analysis, anthropometric design analysis was done, and in case of Chinook, anthropometric design analysis was performed. So, in various types of workstation, various researchers perform different types of ergonomic or human factor issues using digital human modeling software in various times. So, all the research actually carried out in ARL, US Army Research Laboratory. So, among these various workstations, the next few slides we will discuss only on RAE66 Comanche, and this few analysis will be discussed. So, JAX software was used to conduct crew station design, assess anthropometric requirement for female and male aviators, evaluate volume of space requirements for pilots wearing the helmet, assess pilots emergency egress. So, this was actually reported by Kennedy et al. In 2004. So, for detailed information, this particular research paper can be studied further, and determine the optimal location of the rear view mirror based on sight lines available to the pilot seated in crew station of RAE-66 Comanche helicopter. So, these various ergonomic aspects are evaluated in RAE-66 Comanche helicopter. So, in this particular image, it is shown that how line of sight in relation to display position has been evaluated in Comanche crew workstation. Researchers used JAC to assess whether large males and small female aviator would be accommodated by the Comanche crew workstation design while wearing new aviation life support equipment. So, this was actually reported by Kozicki and Gordon in 2002. They observed that the design did not fully accommodate the target population, especially for both the extreme, that is the small female, as well as for large male pilots. So, small female unable to reach ECL. So, here it is shown that for small female it is difficult to reach the ECL. On the other hand, while the large male with insufficient knee clearance, they do not have sufficient knee clearance below the display panels. So, for both the extreme population, that is the smaller female as well as larger male pilots, they are finding difficulties. In this image, it is shown small female position to view the instrument panels, pilot knee interference. So, while pilot is coming out, their knee is touching with the display panel. Similarly, while human model wearing HGU 56P helmet and the helmet integrated display sight system. Then if there is any problem in their performing the activities or in relation to space accommodation, that was studied. Similarly, while pilot is seated on the seat, then through the rear view mirrors, which area is visible, that was also studied in common check workstation. So various ergonomics aspects were studied down the years, and it was reported by various researchers, and all these research were carried out in Army Research Laboratory, USA. We have discussed in various research papers that how digital human modeling software was used for evaluation of air cockpit or passenger seat or spacecraft, and that is also important. Digital human modeling software is also has been used in combination with virtual reality 3D motion analysis system, and these approaches are found to be very effective for not only ergonomic evaluation purpose, also for training purpose, then identifying various problems during maneuverability, during ingress egress. So these are the references which has been referred in various slides. Thank you.